How do I encode that? I say, okay, presence of light, you turning on the torch, I'll interpret it as 1, that's Morse code, right? Absence of light, I'll interpret it as 0. So that's how you decode things at the other end. So I encode it this way at my end, at the receiver end, you decode presence of light, that was 1, absence of light, 0, presence of light. So if I want to send this word, absence of light, 0, 0, presence of light. So based on what word I get across to the other side, you encode things that makes sense. Which means how many bits can I encode per symbol? How many bits can I keep? Turning on the lights is 1. Turning off the lights is 1. So I can only encode 1 bit per symbol with an RZ modulation. Right? So remember, so example, if you had a 50 gigabaud signal, let's use 50 gigabaud as our standard. If we had a 50 gigabaud signal with NRZ, what's the data rate or bit rate I can achieve? I can encode 1 bit per symbol. I give you a 50 gigabaud signal. So it's 50 times 1, gives me 50 gigabits per second, because I can only encode 1 bit per second. Right? So that's the simplest modulation technique that we use. I really don't want to cover spectral efficiency.
I think there was a question.
But there was a question around that. So we will build this concept. So let's say I'm sending a 50 gigabaud signal, and let's say the channel width that I was using, this is all hypothetical, please. This is 60 gigahertz channel, right? With NRZ, I can encode 1 bit per symbol. I can get 50 gigabits per second of bit rate. What's my spectral usage looking like? I can achieve 50 gigabits at 60 gigahertz. So let's say so I'm achieving around 0.8 gigabit per hertz. Just keep this in mind. You don't have to. Now we move on. So how do I achieve higher bit rates? The easiest could be, let's avoid just a 50 gigabaud signal, and let's just throw in 100 gigabaud, 200 gigabaud. Sure, we can, but the problem with that in Byron's explanation is then your spectral usage also. If I want to throw in a big signal, I also need a wider channel that will handle that. So that becomes a major issue. You need more spectrum to do that. But the problem is also, as you add more data into that continuum, you have what's called dispersion. I'll go reverse. I'll explain dispersion. Again, while we're here, why not? Why not explain dispersion? Because without that, then anything I explain won't make sense. Where is dispersion? That's what Byron was saying. This was Mr. Newton doing his thing. Different colors of light are different wavelengths. Right? And the way they travel in a fiber, because a fiber is not just a plain hollow pipe. There's also this concept of refractive index, which you don't have to know. But what you need to understand is longer wavelengths tend to bend less. If you look here, just from here, it's bending a bit less, the longer wavelengths, which means they tend to slightly travel a bit faster compared to shorter wavelengths, which have to bend more. Make sense? So longer wavelengths bend less, they might travel a little bit faster. Shorter wavelengths have to bend more, so they travel a bit slower. See? So it's like us starting a 100-meter dash. Right? We all start at the same time, but the longer wavelengths are your Usain Bolts. The shorter wavelengths are people like me from the mountains, shorter strides, right? Shorter legs. So that's the concept of dispersion. But the problem with dispersion is, this is how the signal starts, but just because how longer wavelengths travel a bit faster, shorter wavelengths travel a bit slower, the light world starts to broaden. Make sense? It starts to broaden. If it's over a shorter distance, fine, not much of impact. But if the distance is longer and longer, that broadening keeps increasing. Problem with that, on the receiver side, as your light pulses start broadening, they start overlapping with each other. So on the receiver side, I'm trying to first detect the signal before I can decode information out of that signal. But if I can't even detect properly which one is the first bit, which one is the second bit, what do you say that in upper layers? In IP world, we say it's bitter. Yes, so that's how we translate. So your dispersion causes errors. So that's the problem. Because of physics, things start broadening. As it broadens over longer distance, they start overlapping. And me as a receiver, it becomes really difficult for me to make out one signal from another. And that is error on the receiver side. Makes sense, dispersion? With that, I will then go back to wherever we were. And hence now you understand this word. So that's the thing. As if I send bigger and bigger signal chunks, because I'm using a very big channel size, things over distance, dispersion starts kicking in. Problem with that, it starts overlapping things, and then I get errors on the other side. So how do we achieve higher bit rates? Because the whole goal is to achieve higher and higher bit rates. Like Byron said, we started from 1 gig. Gig was amazing because I grew up in the E1 days. WIC2T cards, who remembers those cards? That's how we build our pops. Right. My pop from east to western Bhutan, we have a king in Bhutan. He used to be so proud because those days we used to have only, let's say, about 8 time slots. From that, we give a full E1 to one pop. He goes, oh, the internet seems fast. Because one E1 has 30 time slots. Instead of 8 time slots, I'm able to have more. So that's the world I come from, right? And then when the first GP came, amazing. Then came the SFP Plus. Oh boy, it was a big national celebration in Bhutan when we built our first 10G. When we built our first 10G DWDM link. Again, like Brian was saying, the country is only 600,000 people, so we really don't have that much of traffic. So 400 gig is more than enough for the next 10 years, I'm sure, for my home country. So how do we achieve bigger data rates, right? How do we achieve bigger data rates? We can't go crazy with the baud rate or how big a signal we send. So we again go back to basics, we ask physics. There are techniques you learn from the radio folks. The radio folks have been doing higher order modulations for a long time, right? So we try to go into higher order modulations. So with NRZ, you saw that we only could encode 1 bit per symbol. Right? We had only 2 power levels, either no power or there was power, 0 or 1. Right? So next high order modulation is what we call PAM4, pulse amplitude modulation, 4 levels. So instead of, remember the I diagram previously had only 0 and 1? Now we have 4 levels of power. 4 levels of power meaning I can now encode how many bits? No, I can't encode 4 bits per symbol. It's only 4 levels, 2 raised to 2 is 4, so I can encode 2 bits per symbol. So I can only encode 2 bits per symbol.
But you can do it more spectrally efficient.
Yes, you can do it more spectrally efficient. Makes sense. So we are going with high order modulation. There are 4 different power levels. That means with the receiver and me, our Morse code has become a bit more complex now, right? So I could encode at all these different levels, which means I can now encode 2 bits per symbol. What does that mean? For the same example that we used earlier, let's say we continue with our 50 gigabaud signal, right? We can encode now 2 bits per symbol. So what's the bit rate we can achieve? So we have, just by changing the modulation technique, we have effectively doubled the bandwidth because I can now encode 2 bits per symbol compared to an RZ where I could only encode 1 bit per symbol. Make sense? How we achieve. Now, if you look at that, the channel width is still same, 60 gigahertz, because we are still pumping that 50 gigabaud signal. I'm achieving 100 gigabits. Efficiency-wise, I have doubled it. Previously, what was it? 0.8. Right? Again, this is all conceptual. Now, I'm achieving further, I'm achieving about 1.7. Makes sense? Like Byron was saying, there's no free lunch. Right? You want to do this, but then there's no this. But you compare If you compare the signal amplitude of NRZ and PAM4, people call it the I diagram. Forget that. It's the signal amplitude, right? PAM4, it's only just 1/3 of NRZ. Right? It's just 1/3 the signal amplitude. Problem with that, you become more sensitive to noise. More sensitive to noise may result in a tougher OS or not. Again, I've not covered that part. I'll cover it later. Yeah, I'll cover it in a while. Right? Less sensitive to noise, bad OS non-tolerance, which then translates again to errors. So that's why you really can't go crazy distance with PAM4. Right? While it's good, you have managed to double the bandwidth compared to NRZ, but because of how small the signal amplitude is compared to NRZ, you are then limited by reaching distance because your noise tolerance becomes a major problem. Yeah. So we keep asking for this again. So we go, okay, I can't use PAM4 because of that problem. What do I do? If you go back to basics, light has more properties than just the brightness. Right? So you go back and you ask, what else can I use? What else can I squeeze out of light? Right? So far, what have we been using? We have been only using the brightness of the light, the intensity of the light, the amplitude of the light. But light has more properties. One such property of light is what we call phase. What is phase? If you look at that, remember I said light wave is electromagnetic signal. Where is it in that cycle is what we mean by phase. Again, for IP folks, keeping it very simple. So if you compare those two waves, the green wave is ahead of the blue wave by what? 1/4 of a cycle, assuming the full cycle is here. Sorry, assuming full cycle is here, it's about 1/4 of a cycle. If full cycle is 360 degrees, that's about 90 degrees.
Just for everybody, this is where you in high school where you had to do cosine.
Yeah.
This is why you have to pay attention.
I didn't. That's the problem.
Yeah. I'll keep it at your. You shouldn't have bunked classes.
Yeah, exactly.
Right. So again, very simple. A full cycle is 360 degrees. There are 4 quarters. I'm saying it's off by 1/4, so 90 degrees.
Yeah.
So that's what we are trying. Then we say, okay, not just the brightness of the light. Let me also use this property of light properties. Meaning, if I use more properties of light to encode data, I get more data rate at the right? So now let's have a look at what modulation allows us in the brain. Yeah.
I'm gonna stop there. Cool. We can take a quick break. Oh, but 10, 15 minutes. And then we'll come back. Then you'll do a few of Quam business.
Again, I'll keep it very light. For high people.
20 failed trick maths.
Yes,
3D image. It's actually two different sources that come through my 3D glass. Right? Vertical here, horizontal here. My brain thinks it's a 3D image. So we do use this. So we double the bandwidth that way, right? Instead of sending one single polarization, let's send it two polarizations, double the bandwidth. But back to life's lessons of no free lunch. Look at this signal. I just intentionally threw this here. It's a dual polarized 16-form signal. Animation. If you're the receiver, I send you this signal. Are you going to be able to decode anything out of the signal? Remember, you are still a direct detection receiver. What is a direct detection receiver? I can only detect changes in the brightness of the light. Right? So those receivers can't do anything with this kind of signal coming at you. So what do you do? You need a different set of receivers, right? So that is coherence. So what do we end up doing? We end up having to build a different set of receivers. Remember, direct detection is a simple photodiode. All of these changes in the brightness of the light is what I do. But now I'm sending phase, I'm sending encoding data in phase, amplitude, and polarization. Also, that receiver is useless. So we have to come up with a different receiver. That coherent receiver uses a local oscillator, a local laser, and then it mixes it with the incoming signal, and you extract the amplitude and phase information per polarization. That's where the word coherent optics actually comes from. This coherence is same frequency, same phase difference. So every signal that I inject here to mix with the incoming signal, it has to be same frequency as what was coming and the same phase difference. That is coherence in physics. If you didn't miss your classes, those but the word coherent comes from that fact of how waves behave. We don't need to know this. We are IP guys. Hey, all you need to know is where do I plug this? But I'm just saying that that's how it works.
There's not much difference in RF.
What was that?
It's not a big difference between that and RF. Same principle.
Correct, same principle. Because
If you understand microwave, you understand this.
you understand this. Exactly. Electromagnetic wave. So
They actually started this in satellite phones.
So those of us who have come from an RF background have quite a big advantage when it comes to modern optics.
You burst birds.
Yeah. So with that same example that we had before, remember 50 gigabaud with NRZ, we could only get 50 gigabits per second. With PAN4, 100 gig. With 16.4, 200 gig. Now with polarization, 200 times, 2 times of that, because I'm sending it two different polarizations, I achieve 400 gigabits per second. How do you think we build 400 gig coherent optics? Even this.
Actually, I didn't build 800.
But in reality, of course, that was an example that I was using, but in reality, the baud rate is a bit bigger, channel size 400 gig is